Hi everyone, my name is Claire Tomlin. I'm a professor in electrical engineering and computer sciences at Berkeley, and this is the 16th module in a series that we're recording to support the course EE221A, Linear System Theory at Berkeley. The topic of this module is on linearity and time invariance. These are two properties that apply to dynamical systems, the kind and the definition of dynamical system that we introduced in the last module. So in terms of our definition of a dynamical system, we defined it as a group of elements with two associated axioms. So it had an input, a set of input space, a set of input functions, and that's the space of inputs, the state space, the output function space, the state transition map, and an output readout map. And we have two associated axioms with that, which we talked about last day. So the state transition axiom and the semigroup axiom. So if you're given a system with these components and those two axioms, and you can show those two axioms hold, then that's a dynamical system. Now, two important properties that we're going to focus on, and again, with linearity, we're going to spend most of the rest of the course talking about this class of dynamical systems. And with time invariance, we'll spend a lot of the rest of the course talking about this. So these are linearity and time invariance. Now, in order to define linearity, we're going to define another component of a dynamical system, but it's derived from the essential components we have here. And that's what we call the response map, or the output response of a dynamical system. So we define the response rho to be a function, again, it's over the same spaces as the state transition function. So it takes the time axes tau cross the state space, cross the input space, and maps to the output function space. So the way we write this is the output at time t is equal to, as we know, the output readout map at time t, given the current value of the state, or the state at time t, and the current value of the input at time t. Okay, so this is from our state space, and this is from the range space of our input functions. Well, we know that the state at time t can be represented in terms of the state transition function, in terms of a function of the state, so a function of the current time, the time at which the system started, the state at which the system started, and the input function between t0 and t. And that we've still got that u of t coming from the output readout map. And so it's this function here, which now contains the memory of having started at some initial time at that initial state and applied that function u. Remember, this is the function u that takes us, that is defined between t0 and t. So this function s takes the state from its initial value at time t0 to its value at time t. And this is what we define as the response map. So this is rho t, t0, x0, and u. And now this is the function u, the same as the u here, which is the function of u between t0 and t. Okay, we define this response map because it relates, we can think about it as relating to some kind of, well, it's related to the output of the system, but it also contains the dynamics of the system. And typically, in a practical system, we're interested in the input-output properties of that system. The states intrinsic to the system can be defined in many different ways. And so often the outputs have some physical meaning, and that output function represents something physical. So it's interesting to think about that part of the state transition function, which is really, I would say, projected or is part of the outputs themselves. We may not care about all of the states, but we typically care about those states which are important in determining what the output is. So the response function, it's different from the readout map. Remember that the readout map is a static map from the current time, the state at the current time, and the input at the current time. The response function still gives us the output at the current time, but it tells us something about how that has evolved over the time interval that the system has been evolving over. Okay, so this is the response function. Now, linearity is a property of a dynamical system, and it's defined in terms of the response function of that dynamical system. Okay, so we've defined the response as the composition of the readout map and the state transition function. Now let's define what we mean by a linear dynamical system. Linearity. I think we'll switch colors to be purple for linear. So a dynamical system is said to be linear if its response function is linear with respect to two of the arguments, with respect to the initial state and with respect to the input function. A dynamical system is linear if. Okay, so in order to talk about linearity of functions over spaces, we first of all have to make sure that the underlying spaces have a mathematical structure to them, have a vector space structure to them. So first of all, we'll say that the dynamical system is linear. The first condition is that the input, the state space, and the output space all have to be vector spaces over the same field F. Are all vector spaces or linear spaces over, so we use that term interchangeably, over the same field F. And then the second condition is the main linearity condition, which is that the response function has to be linear in two of its arguments, in the state and the input. So we write that as rho at current time, given we started at time 0, and then we'll consider an initial state, which is a linear combination of initial states, alpha 1 x1 plus alpha 2 x2, and an input, which is a linear combination of inputs, and it uses the same scalars. So alpha 1 u1 plus alpha 2 u2. If the system is linear, then the response function has to satisfy the following. So that's equal to alpha 1 rho at t0 x1 u1 plus alpha 2 rho at t0 x2 u2. Okay, so you can see immediately why we need to define u, sigma, and y over the same field F, because it's the same coefficients we're using for the state space, for the input space, and then for the output space. That alpha 1 and alpha 2 are the same in all of those cases. The other important thing to remark here is that linearity is defined in terms of linearity in these two arguments, so in the state space and in the input space. So, and the third thing to note is that linearity is defined in terms of the response function. Okay, so a dynamical system is linear if the input state and output space have this vector space structure over the same field F, and the response function is linear in the states and the inputs. Okay, that's important. You can't just be linear with respect to the inputs, it has to be linear with respect to the initial state. Okay, so that's the definition of linearity, and we can sort of think about some special cases now. We could, for example, think about the zero input response and the zero state response. So if you just think about now in the case of a linear system, we could look at a special case of the response at t, given that we started at time t0 with initial state x0 and input u, that's going to be equal to the response at time t, given that we started at time t0. Given that we started at the 0 initial state, and we use that input, plus, so the same input, plus the response, given that we started at that initial condition, but that we used the 0 input. Okay, so the 0 for the state space and the 0 for the input space, those are the zeros for the corresponding vector spaces. And this is called the 0 state response, or the 0 initial condition response for obvious reasons. And this is called the 0 input response. The response, if you just 0 the input and you look at the response to that initial state. So both of these responses for a linear system, these are linear in their arguments. So this is linear in u, and this is linear in x. Okay, good. So that's how we define a linear dynamical system. And the test is always on the response function. The second important property that we're going to talk about in this module is that of time invariance. What does it mean for a dynamical system in general to be time invariant? And as I said before, systems that are linear and time invariant are a special class of systems for which we can say a lot. We can do a lot of analysis. We can do a lot of computation relevant to these systems. Systems that are linear and time varying are also systems that we can say a lot about, but we can do less computation. There are fewer algorithms that exist to compute solutions to analyze behavior of linear time varying systems than there are for linear time invariant systems. And so let's discuss what we mean by time invariance. And it's defined as a property on dynamical systems. So you can have nonlinear time invariant systems. You don't necessarily have to be linear to talk about time invariance. To talk about time invariance, though, we're going to So essentially, the idea behind a time invariant system is that the behavior of the system doesn't matter on when the system starts. Basically, what's important is the amount of time that the system has evolved from its initial time point. As long as you start at the same initial state for a time invariant system, the response should be the same as if you started at a different time, only shifted according to the difference in time between when you start and when you started previously. And so in order to characterize that mathematically, we first of all are quite precise. We define what's called a shift operator, or a time shift operator. So a shift operator we'll call it, what will we call it? We'll call it t tau of u. So it can time shift signals. So think about u as our input signal, u of t is the function, and we're shifting it in time according to this operator t of tau. And so that's a new signal. It's a shifted u, and it's a function of t. So this itself, so u is a function we started with, t tau of u is a new function. And it's evaluated at t. How is it related to u? It's equal to u of t minus tau. Okay, and so you can apply this t tau to signals y, signals x, etc. It's just a general operator that acts on signals. So if we think about it here, t tau in general, well, in this case, it's operating on our function space u, and it's giving back a new function u. And the way to think about this, I think it's easy to think about it in terms of a diagram. So if this is t, and suppose this represents u of t, so you have some signal, there's some kind of ramp, for example, and that's what u looks like. So this is u of t. If we plotted t tau of u, so this is t tau of u, for some tau, we're going to be shifting. So it's exactly the same signal. Actually, let's be precise here. So I'm going to shift by about, okay, so what I've done is I've taken this signal here and I've just shifted it forwards by tau time units. So we have the property then that the value of the new signal at time t, so the value of the new signal at time t, say this is time t, is the value of the old signal at time t minus tau. So this is equal to this value over here, where this is time t minus tau. Okay, and that's always a good way to test whether or not you've shifted the operator properly, because this can get confusing in terms of thinking about what u of t minus tau actually is in terms of the new signal. Okay, so that's how we define a shift operator. It shifts signals just by some constant tau. So we define a system, a dynamical system, to be time invariant in using the following definition. So time invariance means that so first of all, we have to make sure that the shift operator, when we apply it to an input signal, we still get an input signal back. So we say that the input space is closed under the shift operator. U is closed under t tau. So you start with an input, you shift it, you're still using a valid input to that system. And then in order to define what we mean by a time invariant system, again, we define it in terms of the response function. So we say that the response at time t1, given that we started at time t0 at state x0 with input u, is equal to the response at time t1 plus tau, given that we started at t0 plus tau, with the same initial condition that we started with previously, and with the shifted input, t tau of u. Okay, so everything gets delayed by tau time units under this shift operator. But nothing else changes. So the response itself is the same. It's just shifted accordingly by the amount by which you shifted the input. And so for the system to be time invariant, this property has to be true for all t0, for all valid t0, for all t1, for all shifts tau, as long as tau is so all of these are points in time in our time index, or the time axis over which we defined the dynamical system. So we could define shift operators for both continuous time and discrete time systems. And it should be true for all initial conditions and for all inputs. So for all x0 and for all functions u. Okay, so we have the concept of time invariance, and here we've classified it mathematically as systems that their evolution doesn't depend on the time at which you start. You can shift time and you'll still get the same response as long as you shift the input response accordingly. Okay, so we've given the definition of dynamical systems, which we discussed previously. We now have two important properties of dynamical systems, that of linearity and that of time invariance. And the point to emphasize is that both of those properties are defined in terms of the response function of the system. They're defined somehow in terms of the evolution, or a function which records the dynamics on the output signal. Thanks very much.